Okay, good afternoon, everyone. My name is Steve Hale. I'm a Senior Engineering Manager here at CAE Associates. As part of our e-learning series, today I'm going to be presenting the Workbench Rigid Flexible Dynamics tool, which is used to solve transient dynamics analyses in mechanisms. In case you're not familiar with our e-learning webinars, we offer these at about the rate of once per month. You can view all of our previous e-learning sessions on our website at caei.com, and just do a search on e-learning, and you can view all of those. If you are a New Jersey or New York resident, you can earn continuing education credits for attending the webinar by completing a survey at the end of the presentation. Regarding logistics, the presentation will last approximately half an hour. Everyone is on mute, so if you do have any questions, that's fine. Just enter them into the chat window or the Q&A window, and I'll address those at the end. Just a quick note before we get started, we do have a new website, and it's got quite a bit of additional functionality. We have an expanded resource library with over 250 items and counting. We have a new blog with quite a few very helpful posts on a wide range of analysis topics, so I suggest you check that out. With regards to training, we have a nice calendar that you can use to sign up for training, and then on our CAE University link, you can there's some resources there that you can use to help you determine which classes you need to take. All right. This is what I'm going to present today. I'm going to talk about the rigid flexible dynamics tool, which is also known as a multi-body dynamics software. I'll go through an introduction. I'll discuss the features of the tool, and then I'll go through a functionality demo so you can see exactly how it works. What is rigid flexible dynamics analysis? It's also known, as I said, as multi-body dynamics. It involves the connections of parts via joints to simulate mechanisms. The response is based on the kinematics of the mechanisms, the relative motion between the linkages and the different parts in the mechanisms. There are two multi-body dynamic analysis types that are available in Workbench. There's rigid and flexible. If you use the rigid analysis, all of the bodies are treated as rigid, and you connect those together via joints. So there are a variety of different types of joint connections you can use, and it solves for the dynamic response of those parts relative to each other based on the body inertias, loads, and joint connections. The flexible analysis is very similar, except that any one or additional bodies can be modeled as flexible, and in that case, it still solves for all of the dynamic response of the different parts, but you also are able to extract stresses and strains for those flexible bodies. So, what are the advantages of using this over the traditional method of transient dynamic analysis in Workbench? Well, it reduces the complexity and minimizes the runtime by assigning rigid parts. So each rigid part only includes 6 degrees of freedom, and then they're connected to each other with joints or through contact interfaces. So you can include contact interfaces as well. You can quickly study the following types of behavior: the range of motion in the mechanism, the loads in each joint or contact interface, the effects of springs and dampers, and then part accelerations and velocities. Here are some examples. The first case we have here, a valve, and what you can do in this case, by the way, each of the parts of this valve are modeled as rigid bodies. And in this analysis, you can determine how much torque is required in the motor to close this valve at a certain rate. So if you need to close it quicker, you're going to need more torque than if you can close it at a slower speed. Here's a very simple linkage, and we have essentially revolute joints or hinge joints between each of the linkages. And we have a spring connection between the long arm and one of the shorter arms in there, and then a translational joint down in this at the bottom edge or the left edge of this joint. And by doing this, we can determine the range of motion and how rapidly the linkages move relative to each other. Here is the piston example that I showed you previously. And most of these parts are modeled as rigid, except you'll see that the piston arm itself is modeled as a flexible body, and that's why you see the contours, or the stress contours to be exact, in the piston arm itself. So if all parts are rigid, the analysis can be run as a pure rigid body dynamics analysis. And in that case, it can use the Ansys rigid body dynamics solver. That solver is very, very fast. So it's an explicit dynamics solver. It gives you very rapid turnaround in the results. It's very robust. There aren't any convergence issues that you need to deal with. Joints are used to simulate the body-to-body and the body-to-ground connections. You can calculate forces, moments, displacements, velocities, and accelerations in the joints and in the parts themselves. The only disadvantage of using this solver is that it doesn't calculate any stresses or strains in the individual parts or linkages. If you need that information, you can simply switch any single body to a flexible body, and then you can extract that the stresses and strains. However, in that case, it's going to use the standard implicit solver, and it will run quite a bit longer. So the big advantage of the rigid body dynamics solver is robustness in the solution and speed. So if you're doing, for example, a design of experiments, and you need fast turnaround for the large number of design points you may have, then you'll typically want to use this type of rigid body dynamics solver to get very rapid turnaround. Now here's another case where I've taken the linkage and I've added a contact interface. I've added an additional block here, and then at the top linkage, I've added a contact interface and another contact interface at the bottom of the block. So when that linkage moves upwards, it can interact or impact that block, and it will calculate the impact load on that block, and the block will bounce off. And this, even if you add contact interfaces, it still uses that rigid body dynamics solver. So it still solves quite quickly. Not as fast as if you have only joints in the model, but it still solves quite fast. If you look at the image on the right, you'll see the contact there between that top upper linkage and the block bounces off. Okay, so you can include contact in there. Now, I have a question for you. I just want to get a feel for whether or not any of you have had any experience with any rigid body dynamics type of analysis. Have you used it ever? Have you seen it used? Do you have experience with it, or do you use it frequently? So I'll give you about 30 seconds just to respond to that question, and then I'll proceed with the demonstration problem. Okay. So most of you have never used it, or about half of you have never used it, and then some of you have, about the other half have some experience with this. So I think this is a helpful presentation to demonstrate the capabilities of this tool. Okay. Let me move on with the demonstration problem. What I have here is a robotic arm with a number of linkages, essentially one down at the base, another one connected to that, and actually 3 separate linkages connected to that. And each of these are connected via joints to one another, rotational, or actually revolute joints or hinge joints. And then we have actually a different type of joint at the end. So let me explain what this is going to do. The robotic arm is going to pick up this package on the right, this block on the right side. It's going to pick it up at joint location B. It's going to rotate it 20 degrees upwards. At the same time, at the base, the very base of the arm, where I'm pointing, it's going to rotate that the entire arm 45 degrees. Then it's going to take at the very tip of the arm, at location D, it's going to push that object off the end. It's going to pick it up, rotate it 45 degrees, and push the object off the end. The object is 19 pounds, and my main concern, or one of my main concerns, is the amount of torque required to lift that object in half a second. The other concern is the amount of stress that's getting generated in this base linkage down towards the left side of the arm. In order for me to get those stresses, I have to convert that. I have to change that part into a flexible body. Okay. The way we set up a rigid body dynamics analysis, under analysis systems, you simply drag and drop rigid dynamics out onto the project page, like so. So now I have a new rigid body dynamics analysis system. Here is my model. If I look under geometry and select any one of these parts, you'll see under stiffness behavior, down under details, that's set to rigid. And that's done automatically once you define the analysis type as rigid dynamics. If you needed to switch something to flexible, you can easily switch it here from rigid to flexible. Under connections, we have a variety of joint connections in this model. So we have a fixed connection down the left side at the base. We have a revolute connection. So this is a connection between the base arm and the first joint. So this, what you'll see in the upper left is a series of symbols that show you the degrees of freedom in the joint. Wherever you see gray, that means that degree of freedom is fixed. In this case, we have a blue box next to RZ. That means the local coordinate system that's set up at the joint, and you'll see that right at the joint location, that RZ degree of freedom is free to move. So these two bodies that are connected to the joint are free to move in the Z rotational degree of freedom about that local coordinate system. Okay, so that acts as a hinge. And we can apply loads directly to that joint. I have some other fixed connections in here. I have a fixed connection at this joint. I have another revolute joint out here, which is a little different. If you look at the details of this revolute joint, I have assigned a torsional stiffness to this. Let me change the unit system here. torsional stiffness of 5 pounds/inch per degree, and I have a torsional damping. And that's going to allow a little bit of flexibility in that joint. Okay, I also have a spring here which attaches these two parts at the actuator location. I don't have the actuator explicitly modeled in here, so this spring is inserted in here simply to stabilize the two parts that it's attached to. And you can see these surfaces that are colored. These surfaces that are colored are the two end locations that the spring is attached to. And you can assign a spring stiffness or a damping, so you can include a damper in here as well. Okay. Now I'm missing a couple of joints in here. I need to have a joint that I can use to define the rotation of this base arm, the 45-degree rotation. So I want a connection, a hinge connection, a revolute connection between this base and this first arm. So I click on joints, right-click, insert a new joint. I have to pick a reference side and a mobile side. Now for the revolute joints, it doesn't matter which one I choose as which. So what I'm going to do is I will hide the base body, choose the underside of the first linkage as my reference face. I'm going to show all bodies. Hide the upper body. And I'll pick that face as my mobile face. Now, if I show all bodies, it's going to show me the coordinate system for that joint. So that's my joint coordinate system. The moment the type of the joint is fixed, that means that those two faces will be completely fixed together, not allowing any rotation or movement relative to each other. So I want to change this to a revolute type joint. Switch that to a revolute joint, and you'll see in the upper left, it's showing me that it's allowing rotation about that local z-axis. Okay, so that revolute joint is now set up. Next thing I want to do is I want to go out to the end, and I want to define a translational joint between the tip of the arm and the top face of the package, because I want to ultimately push that package off the end of the arm. So to do that, I'm going to insert another joint. Okay, the reference side I'll pick as the underside of the tip of the arm. So that will be this face right here. Show all bodies. And then the mobile side will be the top face of the package. And once I create this joint, it shows me the joint coordinate system. I want to change the type of the joint to a translational joint. And you notice in the upper left, it shows that local x degree of freedom is now the free degree of freedom in that joint. So that's going to allow the package to slide relative to the end of the robotic arm in that x direction. Now there is a body views tool up in the toolbar. If I click on that, it's going to show me, it's going to give me some additional views of the joint. If I choose sync views, it will sync the views between all three of these windows. And it just gives me some additional tools for viewing that joint. And it's a little easier to see the joint when you look at it this way. Okay. If I look at the mesh, one thing you'll notice is that even though I have a nice green check mark, there are no elements in this model. And that's because all of these bodies are rigid. Under analysis settings, I have to define the step end time. It's going to automatically pick the time step, initial time step, min and max time step for me, and it automatically uses its own time stepping scheme, explicit time stepping algorithm to progress through the transient. I've applied gravity to the model. I have some rotation applied to this joint at the top of the base arm. And you'll notice that this is a rotational load applied to the joint, and it rotates it from 0 to 20 degrees in the first 0.6 seconds, almost 20 degrees in the first 0.5. Okay, now what I want to do is I'm going to insert another joint load, and that joint load will be applied to the arm1 to arm1 base. So I want to assign a rotation at this joint location, at the base of the first linkage. Okay, that's going to be a rotation. I could also apply rotational velocity loads, rotational accelerations, or moment loads. Now the magnitude, I want this to be a nice smooth curve, actually a quarter sine wave type of curve. So I'm just going to cut and paste this functional load. So I change the type of load to a function. And you'll see it's going to rotate from 0 to negative 45 degrees. Next thing I want to do is assign a joint load to the end of the package, or to the package between the package and the end of the arm that will push that package off the end. One thing I can do here, which makes it a little simpler, is I could simply take the joint itself, drag and drop it onto the transient analysis folder, and that's going to create a joint load for me. And the joint load is going to be in the x direction. The type will be a displacement. And again, I want the magnitude to be a nice smooth curve, so I'm going to cut and paste a quarter sine wave type of curve. Okay, so that's going to assign a x displacement in that joint between 0 and 2 inches. Okay, in terms of results, a couple things I want to look at. I want to, of course, look at that torque down at point B, at joint B, where that label is. So what I can do, I can actually take that, actually I'll insert a probe, and that's going to be a joint probe. It's going to be arm 1 to arm 2. That's the boundary condition, or the joint that I want to scope it to. And I want to look at the total moment in that joint. Other thing I want to look at is the maximum acceleration that occurs in the package itself. So if there's some sensitivity of the package to acceleration loads, that's something we can easily track. So I'll insert probe acceleration. I'm going to pick the package body, and then I can solve this. And the nice thing about rigid body dynamics is it solves very quickly. So I'm going to look at the solution information while it's solving. You notice the output is very different from what you would typically see when it runs in Ansys, because it's using that rigid body dynamics solver. So it's a very different solver. And this runs in only about 10 seconds. So much, much faster than it would run if you were running a full implicit transient dynamics analysis with all flexible bodies. Total runtime, you'll see down at the bottom, CPU time, just over 10 seconds. Total deformation, let me animate this for you. that around. And animate. So it picks up the package. It rotates at 45 degrees, and then it's a little hard to see, but at the same time, it's pushing the package towards the end or towards the tip of the arm. I can zoom in a little bit, and you can view that. And you will see also some flexibility in this last revolute joint. There's some rotation in that revolute joint. Okay, let's take a look at the joint probe. So this joint probe is showing me the moment that's occurring in this joint here. Peak moment is about, if you look down at the table, and I'm concerned about that, the moment about the z-axis. So it's about 2260 or so inch-pounds. Right about there. The acceleration probe allows me to track the accelerations in the package. Okay, let me show that again. There we go. And so we've got some early accelerations of about 310 inches per second squared. So almost 1 g of additional acceleration above the gravitational load. Okay. Now, go back to the slides here and ask you another question. Now that we've gone through a few introductory slides and I've gone through the demo, do any of you think this tool might be useful in your work? So I'll give you just a few seconds, maybe 20 or 30 seconds to answer that question. Okay. So good amount of you think that it would be somewhat useful to very useful. So that's encouraging. And just to conclude here, before I go on to answer any questions you may have, I just want to review the advantages of this rigid flexible dynamics tool. It's very easy to use. It's very fast. That's the biggest advantage is the speed. So if you don't need to get stresses or strains, you need range of motion, you need accelerations, velocities, and joint loads, this is definitely the tool that's going to give you the fastest turnaround by far. If you have a lot of design iterations, you're modifying the geometry to determine the best possible design, this again is going to give you the fast turnaround you might need to evaluate all of those different design iterations. You can also add contact. I didn't really cover that too much, but you can add contact between interfaces. It does slow down the solver somewhat, but it's still relatively fast. You can change parts from rigid to flexible bodies if you need stresses and strains. One thing I do want to show you quickly, which I didn't show you before with this demonstration problem. In this version of the analysis, I've taken arm number 1 and I've switched that to a flexible body. Now when I go to mesh that, you notice the entire structure is unmeshed except for that one flexible body. So you can very easily combine flexible and rigid parts in the same analysis. Now when you go into solution and plot a stress, you'll only get stresses in that flexible body. But the solution everywhere in the model is, in terms of accelerations, displacements, and joint forces, is the same. The advantage here is you're just getting the additional stresses and strains. And in this case, I can, for example, pick that one flexible body, hide all the other ones, and then very easily look at the stresses in that one body. And I can pick down here in the table, I can track the maximum, in this case von Mises stress, and retrieve the result at the location where the peak stress occurs, or at the time at which the peak stress occurs. Okay, so that's how you would add a flexible body to this type of analysis. Okay, just going back to the concluding slides. In terms of licensing requirements, if you want to use the rigid body dynamics solver, you need a rigid body dynamics add-on license, which is used in conjunction with a structural mechanical or multiphysics license. If you have any flexible bodies, it's going to use the standard implicit solver, and in that case, there's no additional license required. All right, thanks for your time.